make some remarks on yesterday, and then I'd welcome content questions, with the thought being some of these remarks might stir up questions. Okay, so yesterday we went through a bunch of material that at the face of it, at sort of a superficial level, focused on two main topics. One, open populations. And we actually have to do some fix-up work for one thing there that we didn't quite finish the thought. Number one. Number two, we hit GIS models that include GIS, Geographic Information Systems contents. And there was a lot of learning on sort of model debugging front, but fundamentally the focus there was creating models that include geographic resources. Now that's at the surface level. The truth is, for each of those things, I try to weave in a number of other themes because there's not time to cover them as solitudes. I weave them together so that you're teaching several things at the same time because of the lack of time. So one of them is the fact that we use these things called, well, maybe I'll just mention some major things about those superficial, those high-level topics. So open populations. AnyLogic supports for populations of agents. It supports populations that can change size over time, where we have agents coming in and we have agents leaving. And it's quite straightforward to achieve both. Agents commonly, when they are no longer relevant to the simulation, they disappear. We did that through a thing called remove under bar X, where X is the name of the population in which that agent is located. And they can remove themselves from the population. Agents can come into populations. We did that through add under bar X, where X is the name of the population. They can add themselves, the population grows, remove themselves, shrinks. And there's a little bit of finesse there because that is not obvious. Because, for example, an agent's location within the population can change. Maybe before they were agent 100, and you deleted agent 99, and they become agent 99. Something along those lines, okay? So the numbering of agents, we haven't paid much attention to it, but the numbering of agents, if you're counting this is agent 100, suddenly you delete another agent, they retain their identity. It's just how we name them, how AnyLogic calls them actually changes. If we want to give them a unique ID that doesn't change with change size populations, it's easy to do. After all, we're still referring to them. It's just that their ostensible name in AnyLogic, if you ask it to print out their default name, it's actually based on their location in the population. And so you should be aware that they're agent 1, 2, 3 in the population. That will actually change. Their identity doesn't change. I mean, all their characteristics are the same and so on. It's just how we label them with the default label is changed in how AnyLogic renders it. So sometimes we give them a unique ID, okay? And AnyLogic in recent versions has, I believe in version 7, they introduced unique IDs. Unfortunately, our phalanx is weak this morning. Our TA phalanx. I'm not sure. I'm glad we don't have the Battle of Thermopylae right now. But it would be nice if some more TAs march in. So agents can be lent IDs, and I believe now there's a unique ID that you can summon by asking for its get ID. Open populations have processes commonly associated with them from the health perspective. Immigration. And immigration is easily characterized at the top level because it doesn't involve particular agents. But you have to realize that creating we realize that through an event, and that event fires at a certain rate, but that's not the immigration rate as it's commonly used. It's a hazard rate of sort of when people come into the population. And so 10 would be 10 people a year, not 10 times the population size of people a year. But we used events, and events have come to, kind of in an unassuming way, come to play a big role in our models. I don't know if you know, but they have sort of a lightning shape. And basically, they capture a schedule, a predefined schedule of of one or more occurrences in the typical case. So they can go off, say, at the initial time of a model or final time of a model, or they could go off at regularly spaced times, uniformly spaced times. Or they could go off with Poisson arrivals, so they have a certain chance per unit time of occurring, a so-called rate event. They could be triggered by a rate, in which case it's like a hazard rate. It's a chance per unit time. It's a probability density in the language of mathematics. And 10 would mean 10 times per time unit. 0.01 would be 0.01 times per time unit, or on average 1 every 100 time units, 1 over 0.01. And these events are actually key in building these models. We can use them for regular reporting. Every week, we report the number of incident cases over the last week. Or we can use them to capture processes like birth at the individual level, or like immigration at the global level. It's a very common thing to introduce those. If you had a model of childhood infectious diseases, say measles, you might have a rate event that represents the arrival of people from overseas who are carrying measles. So maybe they've gone to the Netherlands and they bring measles back into your country or your region, and they do so according to some low rate, maybe once a year or something like that. So you can use these events to capture these things. The timing of it, in most common cases, the timing doesn't depend on what's going on in the model. It can be thought of as exogenous. It can pre-compute it. Oh, I'll fire at this time and this time and this time. When it's statically spaced, at precisely periodic, week 0, week 1, week 2, week 3, it's obvious. Or if it's the start time and the end time of the model, it's obvious that that's pre-specified. But even things like Poisson arrivals, in principle, you could pre-plan when it's going to fire. So you could think of it as exogenous in many cases. But there are exceptions. I'm not going to show them here, but events can be set, for example, to go off based on a condition. They go off under the condition that the temperature reaches above 40 degrees, engage in this action, or the air quality worsens below a certain level of healthiness, issue an alert. So you can actually set conditions that do depend on model state with events. And that's very fruitful. It turns out, for those who are interested in something a little bit more advanced, you can disable and enable events. You can kind of say, okay, hey, cool it for this event for now. Maybe an alert has been issued and we disable that for another month so we don't issue alert after alert. So there's actually a lot of flexibility with events. They're an unassuming part of any logic, but an important one. And they often provide an alternative to a state chart, which has an event within it, sort of a rate-based, I said event within it, a rate-based transition within it. So if we had a rate event, it's quite similar to a rate-based transition within a certain state. And so often, like with birth, there's often a choice. Do I implement it with an event, a fertility event, or do I implement it with a state chart where, for example, Jason, we should be getting this on video, right? where we, maybe it is on video. Let's just check the view. It's probably on there. Alternatively, you could have, you know, a birth event, as we did yesterday, or we could have had a non-pregnant and pregnant state chart here, where this is according to some rate. This is a rate, so this is a rate-based transition. Someone becomes pregnant, and then 9 months later, they give birth. This is another way to capture birth. And if you're interested in being able to know, for example, are they pregnant, and having services delivered during pregnancy, or otherwise capturing this delay, maybe this is a delay, for example, of seasonal implications. So Cheryl has guided some really nice quality work on veterinary applications. And here, pregnancy might be occurring during a certain time of the year, say for deer, and you might be wanting to capture that delay between conception and during rut season, and then delivery in the spring or something like that for, say, mule deer. And so capturing this state explicitly is useful. On the other hand, if you don't need this, if you're not interested in service delivery during pregnancy, you're not interested in things that will help improve the health of pregnant women or improve investments in antenatal health, maybe you just want to use a birth event. Whether you use one or another is up to you. Maybe this will be more transparent to stakeholders if you're interested in output involving it. So you notice this gets back to my discussion of scope of model. What I'm thinking about here, the motivations for representing something like this are reflective of what I talked about with scope. Is there an intervention which affects this? Are there model outputs? Or we have to compare it with empirical data, outputs from the model that reflect, you know, something about pregnancies. Do we need to capture differential pregnancy trajectories? You know, so the fact that some pregnancies end in miscarriages or end up in stillbirths or what have you. If so, if there are certain aspects of the causal pathways we want to capture because we want to intervene on them, or because we believe they're key for capturing the phenomena of interest or for comparing with empirical data, sure, you can put it in. Otherwise, go simpler. So we went simpler yesterday. We just used this sort of transition. Another reason that you might prefer this is more of an implementation reason. It's not a deeper reason of scope. It's an issue of implementation, which is if you want age-specific fertility rates, for example. Turns out they're easier to get here than with this. I wish it weren't so. I wish we could just set up birth transitions with a nice schedule of, you know, age-specific rates of firing for a birth event. And as they age, it automatically increments it. But we can't, it turns out, do that so nicely in any logic. Can we do it with an event? Yeah, we could. It just takes some custom programming, and it's more hassle than it's worth. Where you do this is, where you can do it quite readily is with age-specific rates. And all you have to do is set this up to look up in a table. Remember we did that yesterday? We looked up in a table the death rates for a given age. And it took some machinations getting age calculated and all that. But basically, we could look up in a table for someone's age, what death rate applies, or conversely, we could do it for fertility rates and have them transition. Now, the one fly in the ointment is we needed to add a transition like this, which led this to be recalculated every month, year, whatever. It just basically told it, hey, go recalculate this rate so that you're applying the correct rate given their age. Okay, and that's a bit of a implementation detail that at any logic's required just to get it to do the right thing in terms of frequency of recalculating it. So it doesn't apply the rate from, you know, when they're 10 years old for the next 30 years or something. It's recalculated every year, say, or every month. Anyway, so we saw how we could do that with open populations, and we saw, again, this issue of model scope. And in terms of flexibility for age-specific quantities, these state charts have confer particular benefit. They also have some benefits for transparency in terms of being an understandable quantity for stakeholders. We do a lot of work with stakeholders, system stakeholders, health scientists with state charts who have no background in modeling, and they can look at them and they can comment on them and they can critique them and they can suggest things and say you're missing a state or you need another transition, or say you're overcomplicating this, let's just represent it like this. So they are a transparent quantity. Events you can explain and they're fine, but state charts sometimes are a bit more evocative for communicating things. Okay. One thing I didn't talk about yesterday, but was visible in some of the models, I'll just go pull one in, for example. This smoking and heart disease Sydney model that we were looking at, it exhibits something that I haven't talked about. And chances are I might not have a chance to do so for the balance of the boot camp. So I'll seize the opportunity now, seize the day. It's this construct, ladies and gentlemen. This construct right here. I'm going to zoom out here, okay? By the way, for those who have any contacts with the development community, I'll tell you, AnyLogic is built on a popular software development platform called Eclipse. If it seems somehow familiar, if you have any contact with software developers, it's probably because it will be familiar to them. Okay, so here we have a state, this heart disease state. That heart disease state is different than these simple states. Yes, it's transparent. More to the point, it contains other states. The other states are contained within it. It's what's called a hierarchical state or a compound state. I think AnyLogic's term for it is compound state, which is not a bad term. Now, this is a notable feature because it belies the notion that the states as a whole are mutually exclusive and collectively exhaustive. In fact, you can be in undiagnosed and you're in heart disease at the same time. So they're not mutually exclusive. But you'll notice, if you go back in the videos, what you'll find is that I was careful to qualify my statements, at least for most cases, maybe for all during this boot camp. I said all simple states are collectively exhaustive and mutually exclusive. By simple states, I mean these ones here. Once you get to compound states, they're no longer collectively exhaustive, mutually exclusive with others. A compound state is really useful. And there are some models where compound states are used extensively to good effect. I'm going to go open a model that has been around for many years, if I can find it here. And it's a model which makes extensive use of these sort of compound state charts. Alas, I don't think I have it here, but what I probably do have is an image of it. Right. So I'll give up in a minute if I can't easily find it. Here, yeah. This is a model that came out of Cheryl's work, and I'm not sure it warms her heart to see this featured because it's there's a better and more responsive, more performant version of it. But one thing it really brings out is hierarchical states in a very pronounced and a marked way. So what you see here is a real hierarchy of different states that are depicting mule deer behavior. And these states are successively nested in a way that you may find curious. So you have infectious states, and that's divided into subclinical shedding and clinical overt shedding, or you have the seasonal gender-based grouping movements, and they're social movements, and it distinguishes between ones for the summer, ones for rut, etc. Or similarly, this random eat, drink, and for wandering. So what's with all these different nested states? What benefit do you get out of nested states? Where you get several benefits out of these that are quite concrete. And some of them you can see illustrated from here. That's why I actually thought it was worth getting this. One is that you can have transitions into, case in point here, or out of, another case in point, a compound state that express common transitions that, that will apply to the different substates. Okay, so this thirsty transition, for example, any of the simple states in here, these colored ones, could leave due to thirst. But instead of showing a link from each and every one of them and kind of, mind-numbing repetition, you capture the underlying regularity by having a single link from that grouping state. So you place maybe 6, or in this case 4, or what have you, maybe more links with just one link from the overall state, and that's often very attractive. At the same time, you do have the flexibility of having links from particular states within that compound state. So you can still leave from one of these, but you can also have common processes for leaving coming in. Similarly, these internal transitions, these transitions to undertake an action on a periodic basis here, those are going off for either of these states here, okay, without changing which state you're in. And it's quite sweet. Another thing that you can get is you can ask, for example, here, is someone infectious, in the infectious state? And you don't have to get into whether they're in this shedding state or overt shedding or the subclinical shedding. You just ask, are they infectious? And if so, maybe you include them in a certain statistic. So it simplifies the conditions you're using. Instead of getting into are they in state A or B or C or D, as long as A, B, C, and G are grouped into a state, you could just ask, are they in that state? E, call it, capital E. Are they in capital E? Yeah, boom. And then you don't have to get into all the vagaries of what the substates are named, etc. It turns out there's some additional benefits I won't go into. One of them, for example, it has to do with what's so-called history state, where you can go back into a compound state and go back to the particular substate you were in before, for example, that are kind of nice and simplify the task. But these compound states are nice in terms of capturing underlying abstractions. So there's an abstraction here. There's a hidden abstraction. Regardless of whether you have undiagnosed heart disease or diagnosed heart disease, you have heart disease. There's a commonality there. There's a natural orderliness, a structure of it. There's an abstraction. I have heart disease which transcends whether it happens to be undiagnosed or diagnosed. And by grouping it as heart disease, I can have this nice transition there. I can have transitions out. I can summarize it in graphs, etc. So compound states have advantages. And we end up using them a fair bit because of those advantages. We're not going to dwell on them a lot for this bootcamp, but I would argue that they can help make models more transparent yet by cutting down on the unnecessary transitions and capturing and labeling relevant concepts within the diagram. Okay? Compound states. So this was all yesterday. GIS. What sort of extra elements were in GIS? Well, there are some process elements I'll come back to in a moment. But we saw how AnyLogic could place GIS resources at point locations. We saw how it could recognize GIS regions and place resources at, say, random locations within those regions. We saw how AnyLogic has recourse to databases of GIS information that require a little bit of poking around for often locating the resource of interest. So we had to search for clinic and then health and then hospital to find all the places of interest. We saw how it could route people according to car routing or bike routing or walking, footpaths, etc. Transit. We saw how we could set the the movement speed of people and other resources within the model through their properties. So we could say this person moves, say, 1 meter a second. And this vehicle moves 10 meters a second on a highway. Something like that, and achieve that. I'm told by someone who I trust that AnyLogic also supports within a given model some people moving via vehicular routes and others moving via bike and others moving via foot routes. So you can have a mixture of individual types based on their access to transportation or what have you. They move with different routes, and same thing with transit. So it's not one size fits all. I'm told you can actually have it be more specific. Once we had them placed in a GIS environment, the GIS environment could be relevant for many reasons. One reason is they could be influenced by that environment. They could be influenced by the proximity to parks or the nature of the built environment, walkability. And we can use shape files in AnyLogic to give it more information about particular regions. And with the appropriate setup, and I'm not sure if how much would reside in the shapefile, how much separately, you could ask, okay, what is a person in their meanderings through the day? What sort of walkability environments are they exposed to, or food environments? And use that to influence that agent in the model in as much as they engage in behavior or health transitions. So one way is the environment could influence the agents. Another way is the agents could influence the environment. Here you could have agents, for example, polluting the environment. In the model Cheryl led years ago, and now is resurgent, agents shed prions into the environment around them, and those prions accumulate within the environment. Or maybe, buses or trucks with low quality emission standards could pollute that region of it, or a point source could pollute that region. So you could actually capture pollution effects there, which in turn could affect other agents, right? You can have this agents affect the environment affects people. You can have the environment located as a source of resources that are sought in particular cases, like clinics. We saw that case yesterday. People went between their home and their work, and they were exposed. They went to clinics, and they went to the nearest clinic. I didn't show it yesterday, although I'm glad to do so if it were of high demand. Show, for example, how you could ask for resources within a certain distance of yourself, rather than just asking for the nearest one. But it is possible to get information on nearby resources and have the agents make decisions based on it. You could also use it, although we didn't see this yesterday, to ask, find me other agents like me nearby me. Find me other people nearby me, for example, with whom I might interact. So within the GIS context, we have a lot of flexibility, and there's some aspects of it yet that I'm probably not touching on that can be useful. So GIS can be useful for characterizing exposures, impacts on behavior over time, impacts of the environmental consequence of actors in the model, and can be part of this whole agent, environment, agent milieu that we try to capture within agent-based models. Sometimes the environment reveals spatially patterns of emergence that are not clear from simple time graphs. And this is in contrast to what we see, for example, in system dynamics modeling, aggregate system dynamics modeling, and even more disaggregated ones, where our focus is typically on behavior over time as the emergent patterns. Now, when it comes to agent-based modeling, certainly behavior over time is important, but behavior over space is often of great interest. So this is an example of two aspects of emergence. This one here being something that is from a nice built-in model with any logic with a bit of modifications. Here, patterns over space associated with Sherrill's model for chronic wasting disease. And these patterns are emergent patterns. They're aspects of dynamic behavior that reveal surprising patterns that are just as important, in my view, as the patterns we see over time. Time-based reference modes. We have spatial reference modes for agent-based models. And some of the most striking experiences I've had with agent-based modeling have been from seeing these sort of spatial patterns where I didn't expect them. But the truth is they're spatiotemporal. So, they build up over time, but they build up in this characteristic way. Or these waves propagate over time in this characteristic way. This is something captured by agent-based models because of when they have spatial embedding or network embedding, that can be very powerful. You see these patterns over networks or over space, which clue you in to important aspects of dynamics that you would typically miss with an aggregate model, where you might reason about the average contamination over the area in a way that would miss the very salient fact that it's not evenly spread, and some individuals in certain regions are exposed to very high levels and other individuals are exposed to very low levels. These patterns of emergence are important, and visualization helps with that. One final thing I'll note that got into a conversation with Jeff and Cheryl. I had made the point that GIS models are, in my experience, very powerful for communicating some of the essential features of agent-based modeling. Communicating an idea to someone who's just not at all clear about what modeling is and what it brings to the table. It's just one of many techniques for, I think, creating really powerful communication tools. It is a powerful one. It's not the only one. And when it comes to talking with stakeholders to open them up to the possibilities of these methods, it's one tool in the arsenal. It's not, or one weapon in the arsenal. It's not the only one, but it's a powerful one, and it can be accompanied by other ones that are hard-hitting in terms of examples that just clearly demonstrate the need for techniques such as this. So those are some retrospectives about the technical side yesterday. I hope that you will carry away from seeing, well, the disruptions from a technology standpoint that we encountered. You know, the facts that the map didn't work initially, for example, and that we had these cases where I had to close the model and so on. Don't just, I'd encourage you not to view those as simple speed bumps, not to view those as hurdles you got to just overcome and pound your way through. I should have been had better presence of mind to constantly tell you what I was thinking when I was responding to these things. You may have noted that I was animated in responding to these. I was animated because it's intriguing to me and because it's a puzzle that I can solve. But I was also animated because I want to convey to you that when one encounters problems, there's alternatives to just flailing at them. Yeah, and this is a lesson that actually many undergrads in our program, it's very important to help them realize this, that a very important principle with technical problems is don't flail. You know, there's alternatives. There's alternatives to approaching it in a hypothesis-driven fashion, to systematically identify working hypotheses, work to check those working hypotheses, to falsify them by trying things. There's a technique we use to simplify the situation. You try to strip away extraneous detail to see if you could still reproduce it with simpler and simpler cases. If so, it often gives you ideas what's causing it, as well as making it really quick to check hypotheses. You sometimes check, okay, how general is this? Is this occurring with a previous version of any logic? Because it also rules out, oh, it's just it's a problem with my network, for example. It occurs with this version, but not with that one. Okay, it's not just a network problem. It's something probably about this version. Sometimes you work to generalize it, like, would this problem occur with this other model too? If so, it will give you clues to what's going on. Now, all the time that I was debugging those things, I was working with hypothesis after hypothesis, working to rule it out, sometimes using the leading hypothesis to motivate things like switching computers to a different computer, saying, okay, I attach a pretty high probability to this working hypothesis based on what I've gone through, and now I'm going to try it on a new machine. But fundamentally, it's a process that allows those who pursue it, this sort of hypothesis-driven debugging or data-driven debugging, to find problems and resolve them much, much quicker. Studies done of software engineers have suggested a factor of 10 in difference between the debugging time for someone who follows really good practices versus someone who's just flailing. And it's a sorry sight to see our labs, the night before assignments are due, with flailing going on at 2 a.m. and 3 a.m. And it gets increasingly desperate because one's mind is clouded, and the hypothesis, the impulse to form hypotheses is lessened due to being sleep-addled, as well as frustration. And a lot of students just engage in sort of pounding and hope that by tweaking something they can fix it, which is not going to be helpful. So when problems come up, it's useful to pursue them in a structured way, and often you can end up zeroing in much more quickly. I might notice that my thinking there is driven by what are the causal pathways underlying this phenomenon, why am I seeing this, and working to rule out those causal pathways, which not surprisingly, or not coincidentally, is in many ways what I think some of the foremost contributions can be of these models, and foremost contributions indeed of data science and big data, as we'll talk about tomorrow. It's sort of identifying drivers for intervention success or failure and working to improve them, et cetera. So important lesson from yesterday, don't flail. It's possible to perceive these things in a well-defined way. If anyone's interested, there are whole books written for software engineers on how to solve technical problems that come up. There's some wonderful books, such as Debugging by Thinking, et cetera, that detail systematic strategies for approaching problems. And those work very well for models and really can be useful also. This is a very important point. And it's a point that I wish more of my students were here to hear. I appreciate those who are here. These same techniques can be used to learn from dynamic models, to be able to learn what's causing this phenomenon. Is it this thing? Is it that thing that I added? You can really understand why we see emergence much faster if you follow a structured process based on hypothesizing. So, while it may have been frustrating to you, hopefully it was at least amusing to see my animation. But there's a method to that madness. There's underlying that was a pursuit of hypotheses. And if you were to listen back to the videos, you would find me engaged in muttering behavior, at various points, and sort of trying different things that all relate to hypothesis testing and falsification. Okay, so those are some comments from my side. What questions could I answer now from your side about any of this stuff? Questions from anything. It doesn't have to be something we covered yesterday, but things that have come up. Yes, Terry. Mm. Mm. Yeah. Yeah. This is great. Great. Thank you so much for that question. And I'll see if I could find us a model where we could illustrate this with a little bit greater clarity. It's an odd thing that I'm not. Okay, problem. I don't see the models. We've recently been adding here. Hypothesis. I'm using the version of AnyLogic the alternative version of AnyLogic that I went into here. This is 736. Hypothesis successfully demonstrated. Okay, now I'm going to go open the correct version of AnyLogic. Okay, so there's basically two types of these transitions. I'll see if I can show an example just to make it more. I don't want to privilege this side of the room, so I'll come over here. So the two types of transitions are this one, an internal one, and I'll draw it this way, but it doesn't matter what its orientation is. And conversely, one where the transition actually comes out and re-enters the model. Okay. Thanks, Jason. Do you want to get the camera? Oh, awesome, great, thanks. Something like that. Okay. Again, the exact orientation is not important. I mean, this could come out and engage in a whatever. It doesn't matter. So here, the agent is actually not leaving the state. This thing is occurring whilst they're in the state, for example, maybe it's a rate transition, and with a certain rate, while they're in the state, this is going to be firing. Say a rate of, of 1 per hour. On average, once an hour, they're going to engage in food-seeking behavior. They'll consume a muffin. they will consume, a cantaloupe slice. They will consume a Tim Tam. And in the final hour, they will consume a meat pie. So this is a firing transition. It could be this. Another alternative is it could be instead of this, it could be a clock, a timeout transition, right? And however it looks. And here, this would, whilst they're in this state, this is actually going to be firing so maybe this is a timeout, a fixed one per hour. Then on the hour, just like Big Ben, I guess Big Ben is dismantled right now or something. I thought it stopped. It's what? It's getting fixed. Okay. Yeah. So Big Ben is not a good example. But here, once say an hour on the hour, it's going to go off. In contrast to rate, it's just going to go off once an hour on average, and the exact timing of it will be random. It'll be a Poisson process in a technical sense. So it'll be arriving once an hour on average, but sometimes you'll have 2 in quick succession, and they're independent. The timing of each is independent. The inter-arrival times are exponentially distributed, but that's hence this graph. But fundamentally, with a rate transition, we'll be firing on average once an hour, but at different times. This one will be once an hour on the hour. And you can have others, in fact, in here. I suppose in principle, I've never seen it. You could have a message transition or something like that. So while you're in this state, you're going to be doing this. But you're not going to leave the state. You're not actually going to get out of the state. And so you're remaining in there, and this activity is going on whilst there. Here, if we had this, for example, once say an hour, if we had it 1 per hour, you'd be leaving the state and coming back in, okay? Or if it was a timeout transition, whatever it is, it'll be once an hour on the hour. It's actually not necessarily on the hour. It'll be you come in, and then once an hour from then on, it's going to be going. Okay, Jeff would like that, but he missed it. What's the significance of that? Okay, so what? You come back in, okay. So the deal is that there's 2 implications. Implication 1 is that if you have a transition out that's based on something that changes over time, let's suppose it looks up your current age and it picks a mortality rate based on that age. If you're leaving here, say once an hour, it's going to be recalculating this once per hour. So when you enter a state, this is a general rule. Put aside these self-transitions for the moment. The general rule is when you enter a state from wherever, it's going to calculate it's going to try to calculate when you're going to leave via the transitions out. If it's a rate transition, it will actually pick a time when you'll be leaving. You may say, what? How does it pick a time? Well, it knows the fact that it's exponentially distributed with a certain time constant associated with the rate, and it will draw from an exponential distribution and say, okay, you will leave via this unless something else happens to you. You leave via another route. You're going to leave with this one within this certain time. And actually, you'll see this in any logic. Or if it's I'll show it to you in a minute. Alternatively, if it's a timeout transition, it's going to say, okay, you'll specify the timeout. Maybe it draws it from a distribution. Maybe it's a fixed one. And you're going to leave via that unless you leave via some other method, okay? So that's when you enter a state, it's going to try to calculate that. Now, there's times you're going to leave via, say, a message transition before that, and that's all fine and good. It will cancel that event that you were going to leave. But the point is, when you enter a state, it figures out when you're going to leave via the different outflows where it can. The different, don't say outflows. That's going to confuse my students. The different transitions out. Okay. Now, this is going to leave the state and come back in. And so, by extension, it's a good Latin term for it, it follows logically that it's going to do this for all outgoing transitions. I will show you this. Can I show you this? Okay, so that's one implication. It calculates those things. I'll show you that in just a second. The other implication I will also show you. Thank you, Jason. The robot is pointing at me again. Okay, great. Thanks, Jason. Okay, the other implication, so here, it was, by going this, it recalculated the mortality rate by looking up her age in years in this nice mortality rate for age table that we had, right? We defined that in main, and here, by virtue of the fact that we're leaving and coming back in, I'm telling you it's calculating this, okay? Each time. Each time it comes back in, it says, oh, when am I going to leave via this? And it looks, what's my current age? And then it looks it up in that table, and it uses that rate, okay? Now, another thing that happens is this. The entry action and the exit action are computed. Okay? Entry action and exit action here are computed. And what that means is anything that you have in here is going to be executed again. Everything that leaves it. So forgive me. I'm just going to create a model which is going to show this. Lickety split. You folks don't have to follow along, okay? But I'm going to create this. So I will call it demonstration model for self transitions. Okay, and I'm going to have be the unit be days. What the heck? Okay, here we go. Boom. Okay, and I'm just going to put it in main because you can put state charts in main. That's fine. Like different seasons, right? That would be kind of nice. You have the seasons progress in main. You don't need to have a state chart only in an agent, a sub-agent. You can have it in main. Fine. You can have events in main, events in the agent. Different places is fine. You just mix these things together. Okay, here we go. Here's a little state chart. Here's going to be state chart 1. State chart A. How's that? Okay, there we go. Okay, no diabetes. How we do that? Oh, man. I should have used years. Okay, fine. I'll go back to the model. Here, switch the model time unit to be years. By the way, you got to be careful about that if you start putting lots of stuff into the model because it'll remember the old time units, and you got to be careful with that as the default. Okay, here we go. So diabetes to diabetes, to no diabetes. I'm going to put 10 years here. They're going to leave here in 10 years, okay? Okay, and now I'm going to run this model, okay? And I'm going to run it not at its full speed because it will go too fast. It'll go in a jiffy. Okay, so here it's actually pre-planned when this is. Now, you'll notice, man, I should be nuggetizing this, Jeff. You'll notice that this is blue, okay? It's actually figured out when it's going to go. And at that time, 10 years, it switched, right? Okay, now watch this. This is a very useful thing sometimes. TAs, take note. So if I select this, and I say show name, okay, I'm going to show a name. And the name is uninspiring. I'll say developing diabetes. But watch this. TAs, take note. Here we go. Boom. Run. Notice it's a countdown. It's actually counting down until the event goes. Okay? It's pre-scheduled then. It knows, okay, I'm going to leave by that time, unless I leave by another way, which I'm not. And it's counting down to that. Okay? Watch this. If I change this now, well, heck, let's run them side by side. There's no, oh, I copied it. Sorry. Oh, man. Okay. So I copied it and pasted it. So I duplicate another way. I could have selected it and copied with control down. Okay, now this is going to be state chart B. And here, I'm going to have this proceed via a rate transition. And the rate is going to be 0.1 per year. And so on average, it's going to be 10 years until they get that. And this is going to be no diabetes B and diabetes B, okay? And this would be developing diabetes B. Not that these names are particularly significant, and these should be A, but I won't problem right now. Okay, here we go. Okay, TAs, watch this. Yeah. Boom. Boom. Okay? So you notice it's counting down. Did you see that? Did you see that? Watch that. Let's try that again. Should do it with a different random number seed because it was awful. Do you see that? It's counting down. No? It's pre-scheduled that. It drew the timing when it will depart this from this exponential distribution. Then it went. You notice it happened to be much less than 10 years there. If I were to go to simulation and I were to go down and say make it a random number seed, each time it's going to be different. And now sometimes it's going to be more than 10 years, sometimes less, but on average it'll be 10 years until they go. This one still isn't gone because it was exactly 10 years. Try it again. Okay. Okay, now it's about 7 years there. Okay. So it's pre-scheduled then. Now, let's watch this. Watch this. Man, nuggetization is an imperative. Okay. Ladies and gentlemen. Okay. What I'm going to do here is I am going to create a transition. Maybe this is going to bore people, but hopefully not too much. Those posters look good, Christine. Yeah, no, thank you. Yeah, yeah. Okay. So this is going to be external transition A, okay? And every 1 year, it will come out and go back. And I'm going to say trace ln left state no diabetes A. Okay? Excuse me. I meant to put this here. Okay, so left this state no diabetes A. So I'm going to say when it exits here and when it enters state no diabetes A. Okay, and I'm going to change this name of this to be diabetes A. Okay, and diabetes B, A and developing diabetes A. Okay, just to be consistent. Should have thought ahead. Okay, great. So if I run this, what do you think they'll transition down here? Precisely. We'll never hit it. That's my point. Yeah. Yeah, it's going to start again. Precisely. That's exactly what I'm showing. So watch this. See, notice each time it's doing this loop, it's going to re-enter this. It's saying left and entered. And it's never going to leave via this because we keep on leaving this and coming back in. This is going to be rescheduled. It schedules it at the time of entry. Yeah, this is re-entrant, although it's different re-entrance than you have to think about when handling interrupts. But yeah, so it's re-entering this and it's resetting this. Because every time you re-enter the state, it's scheduling. Okay? This is a subtlety. This is a subtlety I'd like Cheryl to be able to know about, too. Because the semantics are quite particular. Okay, now, let's go look, and let's equalize this. Let's make this developing diabetes B. Let's make this a transition. Okay, I'm tempted to make it sure. So let's now let's actually have a C as well. Okay, because I'm actually interested in teaching a couple principles here. So here we go, and okay, and this will be state chart C, state chart C, and Nobot diabetes C, and developing diabetes C, and this C. Okay, now watch this. Ladies and gentlemen, I am going to have this one have an internal transition. Okay? We okay with that? Okay. And I'm going to actually slightly elaborate this. This transition here, when it fires, I'm going to say, I'm going to have an event handler here. Fired transition external transition A. Boom. Okay. Okay, there we go. Thank you, Christine. Okay, and this is going to be called internal transition C. And I'm going to say fired internal transition C. Okay. When this fires. But then I am going to turn this actually into a, whoa, not a message transition, a timeout with 10 years. It's going to go. This one is going to be internal, okay? Okay? TAs, take note of this. Take note. Yeah, it's important to know about. Okay, so here we have it going. Does it ever leave via this? No, it never leaves via this because it resets it. Here, this is going to be firing, and I'm going to have similar code. Whoa. Hey, come on. Is this still connected? I think no, it's still connected. Good. Okay, so entered. I should correct that. The tense of this. This should be entered to be consistent. And this should be left. Okay, and this should be C. C. By the way, notice as a process how I'm using this printouts to debug what's going on. I'm actually reasoning through with this. Maybe to allow us to focus on this one, I'm going to go ignore this one for a minute. Another really useful thing in any logic. Watch this. Watch this. Ignore. Boom. Now it won't even pay attention to it. Sweet. So you could kind of disable it for now. Okay, watch that. Okay. Okay. At first it entered this state. Then it fired this internal transition. What is it not doing? What is it doing that's different from before? When we had this other one, what was different? Well, okay, sorry. I should have emphasized one more thing. I'm sorry. I stand neglectful, and I apologize. Oh, okay. Sorry. I should have made this. What have I forgotten to do here? I should have made this not a message transition. I should make it a, sorry, what am I doing? Timeout, 10 years, just like the first one, right? And this guy has these things when it's printing, just like this one did, right? And this should be showing the name so it will count down, right? Watch this.
counting down. Is it resetting it? No, because it's an internal transition. It's only firing this. It's not leaving the state and coming back in. How do we know it's not leaving the state and coming back in? Yeah, you never see this enter state thing, which we had, left and entered, which I did have for this. So this left it. Now, how about this case? How about this case? Boom. Hey, get over here. I don't want to ignore this. Okay. I'm going to make it a weird shape just so you don't think it has to be the nice shape. Okay. Okay. Here's no diabetes B. Let's copy these things here over to this. Boom. This cries out, Jeff, for nuggetization. Agree or not? Okay, okay. Okay, there we go. Okay, what do you think is going to happen here? This is a rate transition. This is a rate transition. So the first question is that I want to ask, will it be printing these things out when I run this? Will it be printing these messages out? I'll give you a hint. Did it print these messages out? When I ran this, let's unignore it. There we go. Okay, was it printing these messages out for A? You bet it was. Here, I'll ignore both of these for a moment. Ignore them. Boom. There we go. By the way, this ignore thing is pretty handy for experimenting. Don't you agree? Yeah, okay. So yeah, it's printing out these left, entered, all those sort of things. It's printing those out because it's leaving and entering. Does it ever hit this point? If I ran this for years, centuries, empires rise and fall, would it ever reach this? No. It'll be looping forever. Good. Is it entering the state and leaving the state? Yes. As evidenced by that, if I go view console, you could see it. Notice what I'm doing here, ladies and gentlemen. I'm doing controlled experimentation in a simple way. I'm using ignore to hide things. I'm using tracing, this trace ln thing, to print out where I'm getting. And I'm reasoning about where I'm getting. And I'm using the fact that we can have these entry actions and exit actions to states and for transitions and transition actions to sort of trace what's going on at a very granular level, very fine-grained level. Take note of that. And I'm investigating, very clear exemplar cases here. Okay, so here we never get to this point. We leave and re-enter as evidenced by this. We have clear evidence. Okay. And I'm going to ignore these things. State chart B. State chart C. We saw this earlier, right? We saw this one earlier. Does it enter and leave this state? Does it ever enter and leave this state? It only enters it once. Does it leave it and re-enter it every time this fires? No, it doesn't. No, it doesn't. Watch. I'll make the point again. It does not. So here it's going. Okay, it entered it once, as befits it. It came in. Does it ever leave it? No. Does it ever reach this transition? Yeah, it certainly does. Yeah, because it doesn't reset it every time it enters it. See that? See that? Okay. Okay. So now, this final one that I've set up for you, this final one that separates you from the muffins. Jeff, maybe next time you can bring Tim Tams. In case, well, okay, we want to feed them. We don't want to kill them. Okay. So no Twinkies either. Agents of the American Imperium. Okay. Okay, ladies and gentlemen, does this leave this state? Are we going to leave this state and come back in? Sorry? Yeah, it's a good point. Yeah, it's every 1 year, just like the others. Every 1 year, every 1 year, every 1 year internally. Does this re-enter this? Does it ever reach this thing to fire? Does it ever reach that to fire? Riddle me that, TAs. Does it ever reach? Is it going to ever reach this? This rate is 0.1 per year. It's going to take, on average, 10 years. Sorry? It's a distribution. And it's a memoryless distribution, it turns out. So in other words, it's independent each time. Sometimes it will be smaller. Sometimes it will be larger. Sometimes it may be less than what? 1. Less than 1, ladies and gentlemen. Why is that relevant that it may be less than 1? Because this is firing every 1. So, ladies and gentlemen, it will resample from that every time. Will it get there? It will most certainly get there eventually. It will. Yeah, it will. Yes, yes, yes. I leave the proof of that to my TAs. Actually, I'll prove it for you if you don't want it to. But, yeah. It'd be, yeah, 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 yeah. No, it does work. I've got it. So I'll create a proof for that to ensure myself. But yeah. So this is why you never see me using it with this construct. I always do it with. It's always with a rate transition out because it's the timing out via this is independent of this phenomenon. Okay. This is what's going on. I hate to talk about things at this level, but it behooves us to understand what any logic is doing sometimes, particularly if you have this situation where you're doing rates that are age specific and you're having recalculation of them. You want to know that this is going to work and it's going to reach that point. You want to avoid this situation where you have what could be done like this, where you have a period. This last one, this state chart C. Let's unignore all of these. Jeff, I've got to nuggetize that. Okay. This last one. That's just a neat way of getting it to periodically, whilst you're in this state, undertake an action. That's all it is. It's not leaving the state and coming back in. It's kind of like saying, let's have an event fire off here whilst I'm in there. And it works nicely as such. But it's fundamentally different than these two, which actually leave and come back in. But I believe, Cheryl, it's statistically identical if you have a rate transition out, whether you happen to have this transition leave the state, leave the state or come back in. By the way, I'm using my arrow keys to do this. If you wanted to, you could experiment with a state chart D, which further had a rate transition internally, like this. Hey, come on, boom. This could be a rate transition with a rate of 1 per year, and this will be state chart D. Oop, D, boom. This will be D. Cool. and diabetes D. Okay. So you could do this. Would this ever reach here? If I had this, would it ever reach there? Yeah, because it has no problem with resetting this. D is going to get there. No problem. Yeah, all three of these reach here. This one never reaches. Oh, man. Okay, and it could have E. Okay, I better stop myself. But just for my TAs, you should realize that you should be very clear what's going on with each of these, and recognize that there are differences. Like if this were to come out, if this guy were to leave and come back in, and were to be a rate transition, hey, get back there. Oh man. Okay, dealing with truculent transitions is one of my banes. But I prefer it to dealing with truculent students. Okay, so there we go. Great. Okay, so will this last one ever reach? Will the last one ever reach there? It's going to be resetting it. Is it going to reach here in time less than 10? Very unlikely, but let's suppose they run it. It eventually gets there, because eventually it will draw something for this that is greater than time greater than 10, and it will go. But it will take a lot more time than 10. Oh, yeah, okay. Okay, I'll leave that for musing, but these illustrate the principles. Thank you. I think it's time for the break. Terry, though, you had one other question. I did. Okay, good. Let's do that. Let's do that. Sorry? I'm sorry. I'm sorry to inflict it. Yeah. 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 Right. 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 Yeah, with time sharing. Okay, I'm just going to post that. Yeah, well, some people I figured for a couple people in the audience it would probably be worth it. And for the internet audience, ladies and gentlemen, it will be worth it. Okay. So